Hello, my name is Egor Kostylev. I'm from the University of Oxford, and today I'm going to present our joint work with Michael Benedikt, who is also from University of Oxford, and Tony Tan, who is from National Taiwan University. And the title of this work is Two-Variable Logic, well, ultimately periodic counting. So let me start with a brief introduction to logic with Presburger quantification and logic with counting in general. The most fundamental reasoning problem in any kind of logic is, of course, satisfiability or finite satisfiability. And the yardstick here is first-order logic. However, of course, everyone knows that satisfiability is undecidable in this logic. So the question is how to restrict first-order logic so that we can regain decidability. And one of the fundamental attempts is to restrict ourselves to just two variables. And so we come to first-order logic with two variables, f of 2. Here, it is the same as first-order logic, except that now we are allowed to use only two variables, for example, x and y. The key here is that we can reuse the variables. So we can write exists x even in the scope of another x. And now, of course, this x is referred to the inner x rather than the outer x. However, the outer x is also used somewhere else. Here we have decidable satisfiability, finite satisfiability. It is an x prime complete, well-known result. However, what we are missing in FO2 is counting. And to overcome this, another logic is introduced called C2. Here it is the same as FO2, just two variables, but now we can quantify with a number. So we can say that there exists exactly 5 x's such that subformula after it holds. This has the same complexity of satisfiability, finite satisfiability, and x prime. However, the question is, can we go any further? And the key question for this particular research is, can we check that a graph is Eulerian, meaning that each node in this graph has even degree? It's not difficult to see that this is not possible to check this property in C2. However, to do this, we can use Presburger quantification. What it is? Well, let's start with linear sets. These are basically sets of natural numbers which form arithmetic progressions. For example, like a plus p is the set of numbers a plus p, a plus 2p, a plus 3p, and so on and so on. For AP are the natural numbers. For example, 4 plus 3 is 4, 7, 10, 13, 16, 19, and so on and so on. Now we can generalize this to ultimately periodic sets or semi-linear sets. They are finite union of linear sets. And we write them as just a set rather than union and omit 0 periods. So we say here just C1 rather than C1 plus 0. What is good about ultimately periodic sets that they are, the set of them is closed under complement and intersection. More importantly, these are precisely the sets of natural numbers which are expressed by unary Presburger formulas. I will come to Presburger arithmetic in a minute. In the paper, we also consider this infinity as an ultimately periodic set, but for the sake of this talk, we don't bother about it. So what is Presburger quantification and what can we do with this? Well, it's generalization of counting, of course, because now we can have exists S x phi, where S is not just maybe a number as in C2, but maybe an ultimately periodic set. And here we can have quite nice equivalences. For example, we can express false bottom as exists empty set x is phi. Empty set is the union of 0 linear sets. Also, we can write exists 0 x's. This is the universal quantification. So 0 x is phi, meaning for all x is not phi holds. And also we can even express negation using the nice property that the complement is also an ultimately periodic set. So all natural numbers is an ultimately periodic set. So we can say n minus s, and this will be the negation of the formula. Okay, so what about logics with this Presburger quantification? They are studied For example, FO1 with Presburger quantification, first order logic with just one variable. We have decidability for satisfiability. Model logic with Presburger quantification, again, a little bit more expressive stuff. But for the sake of this paper, we consider full FO2 with Presburger quantification. So first order logic with two variables and Presburger quantification. In this logic, we can express a Eulerian graph. For all vertices X, there exists an even number of Y's, 2 plus 2 is basically all even numbers, such that edge XY holds. And the main result of this paper is that satisfiability, finite satisfiability in this logic are both decidable. And next, in the rest of this talk, I will present some ideas how we can prove this result and also what kind of consequences do we have for other logic problems. So the main ideas for the main result. The idea is actually to translate to existential Presburger arithmetic. And translation is based on biregular graph method, which was introduced by Tony Tan, one of the authors of this paper, and Eric Kopczynski a few years ago. Importantly, we have the same formula, same Presburger formula for both satisfiability, finite satisfiability. So in the rest of the talk, we concentrate only on finite satisfiability. All right, and briefly, what is this existential Presburger arithmetic? Well, they are, I'm sure everyone knows, but anyway, so there exists x phi of x, where phi is a first order logic quantifier free formula over the signature, special signature plus less than 0 and 1. And what is important here is that we interpret these formulas always over just natural numbers with the usual meaning of the symbols. And here, satisfiability, which is in fact just model checking, becomes decidable, and this is well-known result. It is in and P. Right. So how do we do our translation? What are the main steps? The first preprocessing step is translation to Scott normal form. This is a very standard method for standard preprocessing for logic with counting. So what's here? Well, of course, it has a little specific things because of the logic we consider, but the main ideas are standard. So here a formula in our logic is in Scott normal form if it is of the following shape. Universal part for all x for all y, alpha xy, where alpha is a quantifier-free formula over x and y, so it may have a little structure inside, conjunction, disjunction, maybe even some unary component for just x or and for just y, but no any quantification, and more complex conjunction of several components of this form. For all x exists some semi-linear or ultimately periodic set Si, y such that beta holds. Importantly, beta here is just an atom, so it's not any other structure. It's either Rxy or Ryx. Also, we require that x is different from y. Additionally, one more requirement is that all periods in all S's we have in our formula, we say they are either some of them are zeros and some of them are common P, which is common for all the formula. And this simple lemma, standard proof, says that each formula in our logic can be transformed to Scott normal form. Proved by just giving names to subformulas as usual. How to achieve a common non-zero period? Just take the least common multiple. Right, so our result boils down to the following lemma, that each FO2 press formula in Scott normal form can be translated to equisatisfiable existential Presburger formula, which is equisatisfiable. Now I need to introduce some terminology. First, I want to talk about one types, two types. These are standard things. One type is a maximally consistent set of atoms and negated atoms over one single variable x. So describes elements locally in the structure. Two types, they are maximally consistent sets of binary atoms and negated atoms over two variables x and y. So they are describing two different elements. We require that each two type includes x different from y. So we really describe two different elements in the structure. The next notion, so-called behavior function, is a specific notion for this work. And what it is a function from two types and one types to a set of linear sets. Don't bother much about this particular linear set. What is important about here is that it is finite, so we can describe all behavior functions, like just list them, there are a finite number of them, and that they cover all natural numbers. So all natural numbers belong to one of these linear sets. Of course, they depend on the specific formula we consider, but basically it capture all these behavior functions, and this set capture all relevant cases we bother about. Okay, so why do we consider these behavior functions? Basically, the intuition is that each element in each finite structure belongs to a specific set A pi G for one type pi and this behavior function G. So given an element, we take its one type, it is pi, and we take its behavior function, which basically describes how this particular D relates to all other elements in our structure. And having D, we have a unique A pi G. We have a unique pi and G. So all the structure is separate, partitioned into these sets. Just an example of this behavior function and this A pi G. So let's consider one element D, this little graph, this little structure. What is pi G for this element? Well, first of all, what is the type of it? It is C. So we write C of X as a pi. But also, what is the relationship to other elements? We have like 7 elements here. Well, we have 2 elements which are connected from D by E, and both of them are in C. So we have 2 here for the value of the behavior function of this D. And here the 2 type is EXY. This is this edge, and not EYX. So there is no any backward edge. And C of Y is the type of the end of this edge. 2 of these guys, one guy were the same, except that now we have not C of Y, so the end is not in C. One element, so that the E is in the other direction, but with C. So we have here not EXY and EYX, C of Y. It is one element. And 3 elements which are not connected to C at all. Not connected, we have not E, not E. Also, they are not in C, we have not C at the end, but also we have 3 plus 5 here. Why 3? Okay, there are 3 of them, of course, but why plus 5? Because here we have a, for example, the maximal offset is 2 in our original formula, so we can put plus 5 as the period. If we have like 8 elements like this, we will have the same, 3 plus 5. Would we have 4? It will be 4 plus 5. And all other value for all other 1 types of G are 0 because we don't have any other elements. Right. So let's come back to our translation. How do we do it? Well, we have the formula in Scott normal form, and there are 2 components of it, alpha and this more complex stuff. And our Presburger translation again have 2 components corresponding to each of the components in the formula in the Scott normal form. Consist 1, consist 2. The variables we need, the existential variables, Presburger variables, we have 1 variable for each 1 type and each behavior function. Okay, and the intention is that the value for this variable is precisely the size of this A pi I Gj. So precisely the number of elements of type pi I, which behaves towards other elements according to G sub j. All right, so how can we now translate the 2 components of our Scott normal form formula? Well, the first one is quite simple, right? So we have for all x for all y, alpha xy. What does it mean? We basically say that for all x for y, alpha should hold. And we basically look at the variables and the components pi and g and need just to forbid those pi's and g's, which altogether may imply not alpha, meaning that, well, formally, 1 type and of behavior function are incompatible if there exists some e and pi prime such that the value of g is non-zero, and altogether pi, e, and pi prime imply not alpha. So if they imply not alpha, then g must be zero. Okay, let's move to the second part, and here it's a bit more complex, but first idea is kind of similar. Now we have that beta, remember, it is just an atom, a binary atom. So really we don't care about pi, about one type, which talks only about unary stuff essentially. So we care only about g's, about the behavior functions. And what do we need? We need that overall for each element, its behavior function is such that the component, well, all the e's and for all pi primes, which imply beta, the overall, the number of neighbors is inside S sub I. So formally, we call like a behavior function good if for all i's, for all part of this component in the Scott normal form, we have that the sum over all e's, all two types implying beta, and the sum over all pi primes, which are kind of just sum irrelevant here. The g gives us a value inside S sub I. But the problem here, well, this is nice and simple, but the problem is that, okay, what we really described, we said, okay, the elements of type pi have appropriate number of neighbors for each two type. Elements of other type have also appropriate number of neighbors. But we are talking about edges between different elements, right? And they need to coordinate, saying that just some number, good number from one side, one number of another side is not enough, right? So we need to coordinate. And the key observation for this paper is that we need to coordinate, it's enough to coordinate only for each pair, specific pair of one types. So we can basically look at only elements of one type, elements of another one type, and coordinate between them. And this is precisely what's going on here in the other component of consist2. We say, okay, we have two cases here. One is when we have a pair of one types which are the same, and this is one subformula, and the pairs which are different, this is another subformula. And how to deal with them? Okay, it's pretty much similar. So we consider only the case when we have two different one types. So basically we consider elements in our model which have one set of elements of one type and one set of elements of another type, which are different. Then consider all relevant variables here. Well, of course, you may notice that this formula is parameterized by some else, and these are some matrices, and they are have quite complex structure. Don't worry about this structure much. What is important here is that they represent the behavior functions, all behavior functions. Well, if we talk about L pi 2, behavior functions towards pi 2. So when looking from pi 1. So we have pi 1, element pi 1, it has some behavior functions, and the values of it towards pi 2 are described by this matrix. And opposite direction, from looking from pi 2 towards pi 1, we have another matrix. Okay, so this is a bit complex. What is important here is that actually the lemma says that this formula should basically say that the substructure over all elements of these two one types, pi 1 and pi 2, should be a bipartite graph of some specific structure. It should be complete, it should be edge-colored, and correspond to these two matrices. So let's have a look at it a little bit in more detail. So what is a biregular edge-colored graph? Well, we'll start with this. This is pretty much standard. We have a bipartite graph. We have two sets of nodes, U and V, and then we have a bunch of colors. It is complete, meaning that actually each pair, UV, has a specific edge, one color, each pair. So everything is there. And then this graph is AB biregular for two matrices A and B of these linear sets. If U can be partitioned as to some m number of parts, and v as well, so that actually for u, the EI degree for this particular color EI of each node in UK is AIK. So we have a matrix A, which basically tells us for each component of the partition of U, how many neighbors do we need on the V side for each color E sub I. And precisely the same from the other side, from V. So these are biregular H-colored graphs. And the key lemma of this paper is that there exists a Presburger formula that holds if and only if there exists an AB biregular graph. Well, the formula, of course, depends on A and B of the particular matrices, and the free variables, they give us precisely the sizes of the partitions of U and V. Okay, so overall, we have the following picture. We have a formula in Scott normal form. We translate it to existential Presburger formula. Scott normal form, 2 components, universal and complex. Presburger formula, again, 2 components. First is simple, second has these coordinating parts. The variables are a variable for each one type of an element and each behavior function for which describes the relationship to the other elements in the model. Okay, so let me very briefly give you some idea of how to prove this key lemma of that we can describe biregular graphs with a Presburger formula. I will make a couple of very strict simplifications. I will talk about just one color. I drop completeness and I drop periodic values. So now we consider A, B are now just vectors of numbers, C1 to Cm, D1 to Dm, and we ask whether U can be partitioned, so nodes in each component is the degree of each node in each component is just an element in A or B. And here we have our lemma, which is actually proved by Tan and Kapczynski in the paper I mentioned, that we really have this formula. Very briefly, what do we need? We need a Presburger formula checking existence of a bipartite graph with appropriate degrees, as I said. And the necessary condition for this is that actually the dot product of X and C must be the same as the dot product of Y and D. So basically, what is the dot product of X and C? Is the total number of outgoing edges from one side, from U side, and on the other, on YD is from total number of edges from the other side, right? And it's obviously necessary. We must have the same number of edges from both sides. It is a bipartite graph. Apparently, this condition is necessary, but it's also sufficient provided the sum of C's is big enough, where exists a constant which bounds when we can guarantee that this is a sufficient condition. So overall, well, since C is kind of given for us, it's not a variable or whatever, we can just list all these cases in some clumsy but finite disjunction of small cases. And the rest is just, of the formula is just like saying that this condition and the sum is big enough, more than C. And the proof that it is sufficient condition is quite simple. Okay, that's it. Let me conclude with some observations. First of all, we have shown that satisfiability and finite satisfiability in first order logic with 2 variables and Presburger quantification are both decidable. Well, you may ask me, what is the complexity of this? Well, our algorithm probably can give us to nx time upper bound. However, well, we still need to check all the details for this. Nonetheless, this is not a matching known lower bound because the best lower bound we know is nx prime, which is taken from FO2 and C2 as well. So to close this gap is our future work. However, we can say that data complexity is NP complete. Finally, the corollary is that the spectrum in this, the spectrum problem in this logic is actually Presburger definable. So basically we can say that the set of sizes of universes of all models in this logic, we can write a Presburger formula for this. How to do it? We just need to sum up all the variables in our formula. Okay, thank you for listening, and I'm sure that my colleagues are ready to answer your questions. Thank you, and bye-bye.